Welcome back to another explainer, folks. Today, we're stepping into a fascinating, highly controlled, and largely invisible world that we all rely on but honestly rarely get to see, the diagnostic laboratory. I mean, when you hand over a medical sample, you just trust that the results coming back will be flawlessly accurate, right? And that the people handling those materials are perfectly safe. So today, we're going to break down exactly how science ensures absolute precision on one side and maximum human protection on the other. Okay, let's dive into this. We're building this explainer on a dual-pillar framework of quality and safety. First up, the quality management system. Then, standardizing laboratory procedures, followed by the anatomy of lab errors. After that, we'll tackle biosafety versus biosecurity, and wrap up with handling hazards and emergencies. Section 1, the quality management system. Precision and control. To get those reliable lab services, you really can't just hope for the best. You need an overarching, highly organized framework. Now, you might be wondering how we actually maintain that control. Well, in the world of QMS, there's this classic exam trick that trips a lot of us up, and it's the difference between quality control and quality assurance. Quality control, or QC, is super specific. It monitors the testing process itself and uses control materials just to detect analytical problems. But quality assurance, QA, is the whole shebang. It covers the entire system from the moment a test is ordered to the moment the result is delivered. Basically, QA is designed to prevent errors from happening in the first place, and QC is actually just one small piece of that much larger QA puzzle. Moving right along to Section 2, standardizing laboratory procedures. This is our blueprint for quality. If QMS is the macro view, we now need to zoom into the micro view, the rigid rules that keep a lab running day in and day out with absolutely zero variation. If you've spent any time in a regulated lab environment, you know these three letters. But let's pose that classic Viva question that always seems to pop up. What exactly is an SOP? Well, an SOP is a standard operating procedure, but it's really so much more than just bureaucratic paperwork. It is an authorized written document that gives us highly standardized instructions for performing a specific procedure safely and consistently. Think of it as the literal blueprint of the lab. By standardizing exactly how a test is run, SOPs cut out the variation, they improve reproducibility, and ultimately, they prevent catastrophic medical errors. But what happens when that blueprint gets ignored? Let's move to Section 3, the anatomy of lab errors. This is where we look at where things actually go wrong. Let's see how this builds across the testing life cycle. Because laboratory errors aren't just a giant messy pile of random mistakes. They're traditionally and very strictly categorized by the exact time they happen. We've got the pre-analytical phase, which is everything before testing, the analytical phase, which is during the test itself, and the post-analytical phase, meaning everything that happens after the test is done. Let's look at a highly relatable example here. Imagine a patient needs a coagulation test, but whoops, the phlebotomist accidentally draws their blood into an EDTA tube instead of a citrate tube. The machine hasn't even touched the sample yet, but guess what? The test is already completely ruined. Because this happened before the actual testing process even started, it's a textbook pre-analytical error. Identifying the exact stage of the error is absolutely crucial, and here is a fantastic trick to keep in mind. A lab result can be analytically perfect. The machine worked flawlessly, the reagents were fresh, everything was spot on. But it can still cause massive patient harm. How? Well, if that perfect result is reported to the wrong patient, that means a pre- or post-analytical identification failure completely overrode that analytical perfection. Wild, right? And this brilliantly illustrates how laboratories actually respond to these kinds of slip-ups. It comes down to corrective action versus preventive action. If an error manages to slip through, say your QC fails, you take corrective action to investigate and fix the problem that just happened. But the ultimate goal of any lab is preventive action. That's when you identify the root cause of a potential nonconformity and eliminate it before it ever has a chance to happen. All right, that covers the precision side of our explainer. Let's shift gears to Section 4, biosafety versus biosecurity, the pillar of protection. We're going to look at how the lab keeps its personnel and the public safe from the hazards inside. Now, these are two terms that sound practically identical, but they are fundamentally different beasts. The easiest memory trick here, it's all about intent. Biosafety is all about preventing the accidental exposure or release of biological agents. Think dropping a test tube on the floor. Biosecurity, on the flip side, is about preventing the intentional loss, theft, misuse, or unauthorized access to those agents. So, biosafety is accidental, biosecurity is intentional. Now, what's really interesting about this is how we scale that protection based on the actual danger of the pathogen, using 4 biosafety levels. Down at BSL-1, we're dealing with minimal hazards that just need basic practices. BSL-2 steps it up to moderate hazards, and this is where most clinical labs operating with human specimens sit, requiring restricted access and PPE. Then BSL-3 is a massive jump. It deals with serious airborne risks, which means we need enhanced containment. And finally, BSL-4. That is maximum containment for incredibly dangerous, life-threatening agents where there might not even be a cure. Knowing those containment levels brings us right into Section 5, handling hazards and emergencies. Because despite every QA system and biosafety protocol in the world, we have to be physically prepared for the real-world risks of a lab environment. Let's ask a super practical question about that physical environment. Why exactly is a biological safety cabinet, or BSC, used? If you've ever seen a tech reaching into a large glass-fronted machine, you've seen a BSC in action. But what is it actually doing? Well, a Class 2 BSC is our primary containment device. It provides protection for the personnel, the environment, and the product itself. And it pulls off this engineering marvel through highly controlled airflow and HEPA filtration. It physically traps and prevents infectious aerosols generated right there during testing from escaping into the room and being inhaled. But hey, biological aerosols aren't the only thing we have to worry about. Labs are packed to the brim with flammable chemicals, gases, and high-voltage equipment. Fire and general hazard awareness is absolutely critical. You literally must always know exactly where the fire extinguishers, emergency showers, eye wash stations, and spill kits are located. And of course, you must immediately recognize the universal biohazard symbol. Missing it or ignoring it can honestly be fatal. Now, if a chemical spill actually does happen, labs have a rapid-fire sequential protocol that we follow to the letter. First, you alert the people in the area. Second, restrict access. Third, get that appropriate PPE on. Fourth, and this one is vital, follow the chemical's specific safety data sheet, or SDS. Actually, you can never just assume every chemical uses the same neutralizing agent. Doing that could literally cause an explosion. Fifth, use the correct spill control materials. And finally, dispose of the waste properly and report the whole incident. So we've seen how standard operating procedures provide us with a rigid blueprint, how quality management systems catch and prevent errors, and how biosafety levels protect us from invisible hazards. But it leaves us with a fascinating, maybe even a slightly unsettling question. In a world of incredibly strict SOPs and maximum BSL-4 containment, is human error the only variable that can never truly be engineered out of the laboratory? Think about that the next time you see a medical test result. Thanks so much for joining me on this explainer, and keep questioning the science around you.